All right, let's get things started. Hello, everyone. You see me? Can you hear me? Is anybody out there?
Yep, we can see and hear you.
Okay, cool. All right, let's just jump into it, I guess. So the mock test 2 is posted on the class webpage in case you guys haven't seen it yet. So I mentioned the topics that you should study in order to actually try it. So study first, and of course, pretend it's a real test and take it like a test and see how it goes. And we can probably follow up with that on maybe even Friday. So maybe you guys can do some studying today, try the mock test tomorrow, and we can probably discuss it on Friday because we are pretty much wrapped up. There's a few more things I want to talk about besides integration by substitution, and it should be, if I don't get to it Friday, talking about it on Tuesday is fine for me. So yeah, we can discuss the mock test or any issues you guys have with it on Friday. And so yeah, you might want to take it by then so we can discuss it. So that's an option for Friday. If not, I'll just move on to the other stuff I wanted to talk about, but it's not terribly important. That being said, let's actually jump into it. Let's share this guy. So here's our OneNote stuff, and hopefully you guys saw the lecture that I posted. I believe it's already up. We had some technical difficulties last time. I stitched the videos together and I uploaded it. And in the description of the videos where you'd find a PDF of these notes. So some of these things that I've been typing, we might move too fast for you to actually write them down. But of course, when you open the notes in the PDF, you'll see all this here. But of course, whenever I'm writing with a pencil, I would assume that you are as well. There's definitely a benefit to taking your own notes. So to continue here, we were talking about integration by substitution. This is just a technique to compute integrals, right? So there are times when we can use our basic rules to compute integrals, and for this class, I think these are the only ones we need to know. Sometimes you can't apply them directly. You can simplify and then you can apply them, but there are other times when you can't simplify and you can't apply these rules. And in this class, whenever you're in that situation, the option is always substitution. We're not going to learn any other integration techniques other than substitution. That's the last thing. So if you can't apply a basic rule and you can't simplify it so that you can apply a basic rule, substitution is what you're going to do. So what is integration by substitution, right? So that's the method that we described here. And basically the idea is you're going to substitute a single variable for an expression in your integrand, and hopefully in doing so, you're going to make the integrand simpler. You're going to change all the variables. Normally we'd use u. A lot of students call this u substitution, but you're not married to u specifically. But it's customary to use u. And so you just say u equals this expression. That's making this thing complicated. Then you're going to compute your du. You're going to plug those guys into the integral, and you're going to get a new integral. And hopefully that integral puts you into one of these two situations where you can either apply a basic rule right away or simplify and apply one right away. You can find the answer in u's and then convert back to x's at the end. So we did a couple examples of that. So this was one guy. That was a guy that a basic rule does not directly apply to, and we can't really simplify it because we can't distribute a radical or anything of that sort. So the option here was substitution. That's always what's to be the option. So yeah, we worked through that. The guy under the radical was making things complicated because if that were a single variable, I would just write the radical as a power and it would be no problem. So I decided to make what's under the radical the u, and I have to compute the du, which is just me differentiating. That will help me replace the dx. And ultimately, it turned into another integral, which was a lot simpler. And we did a second example. And what we're going to do now is go through these three. And I asked you guys to try these for today. Tomorrow is now. And so that's what we're going to do. So maybe at this point, let's do this one. Let's do problem C. And maybe someone can tell me what they actually did for this one. Ideas? Oh, that's cool. The dog is in math class. You should test him on substitution. Ask him to quiz you. Okay. All right. Go.
Oh, okay. So u is going to be equal to 4 minus x.
Right. So this guy here is kind of making things complicated, right? So of course, if it were this, that's easy, right? Because you can just rewrite that as a power. But the fact that the sum under the radical makes it complicated. So you want to identify what is making your life harder. You can't really, dealing with the sum is difficult. So yeah, so probably u equals 4 minus x is going to be a nice choice. All right, so now that you've chosen that, what else?
You find the derivative of u, so that would be negative dx.
Right, then?
Then you just modify that to have dx equals to du over -1.
Right, or negative du, same thing. And then what?
Then you just plug in u into the equation.
Okay, so what does your integral look like?
1 over square root of u, and then du over -1, or negative du.
Yeah, all right, and then?
And then you just find the antiderivative, so that would be square root of u over 2 times -1.
Well, we can move the -1 over here. But yeah, square root of u over 2, how did you get that?
So I added 1 to the power, so.
Oh, but you didn't write it as a power yet. So that's what I mean. I think you skipped a step. How did you write it as a power?
U to the -½ power.
Right, so this 1 over radical u is u to the -1/2. Okay, and now you can do the power rule. Add 1 to the power, you get 1/2. Divide by the new power. Dividing by 1/2 is the same as multiplying by 2. And so we have that. And so that's the integral. The problem is here, it is in u's when the original problem was posed in x's. So what do you do here?
You can factor out the 2.
From where? We're on this line?
Yeah. Right?
Factor it from where?
Just put it outside of the integral sign.
There's no integral sign. You already did the integral. Right? And this is your answer here.
You just plug in the original equation, so it would be 2 times 4 minus x.
Right, so -2 times 4 minus x to the 1/2. And that's your answer. Or if you prefer, you could write as -2 times the radical of 4 minus x. It's the same thing. Either way, you will realize that if you were to differentiate this, you would actually get the guy that's up here. You would actually get this part. So yeah, that's actually correct. And that's substitution. All right, let's go with the next one. Maybe someone else want to try this one? So this is this here, just recopy it larger, 3x divided by 5 plus x squared. Any ideas for that one?
U equals 5 plus x squared.
Okay. And then?
You find the derivative of that, so that would be 2x dx. And then you rearrange that to have dx on the left side. So dx equals du over 2x.
And then?
You plug, can you plug that into the equation?
Okay, so what's it going to look like?
3x over u time, well, and then dx, or no, du over 2x.
Right. So at that point here, we have that our u was this guy. So I'm just going to plug that in here. And then we also had that our dx was this guy. So I'm going to plug that in here. Now the 3x was not replaced by anything, so he just stays. But ultimately what would happen here is that the x would cancel the x, which is what you want because you only want the u's to be there. The moment you're mixing x's with u's, that's bad. That's no bueno. You want to actually have only one variable. So you have all x's or just all u's, right? You can't actually make a move if you have both variables in play. And that's a big deal when it comes to choosing your u. If you choose a u in such a way that after you plug these guys in, you have x's left over, then what that means is that the u you chose was not the right one. So we can clean this up a bit. So 3 and 2 are constants. I can move those guys outside. And ultimately we have that. And what is that integral?
ln times and the absolute value of u.
Right, so it's 3 over 2 ln absolute value of u plus c. And yes, the absolute values are important. And now we do the same thing. So this is the answer, but it's the answer in terms of u's. We always like to give our answers in terms of the original variable, which is the x's. So all we do is we just actually plug in our u is this guy here. So we're just going to plug that guy in. So then it becomes 3 over 2 ln of absolute value of 5 plus x squared. Now, yes, in this particular situation, you can ignore the absolute values, but that's only because the inside is positive. So, however, there's potential to be wrong if you don't have the absolute values. That's if the inside could hit negative, because then your ln won't behave. So keep the absolute values. It's never going to be wrong if you just leave them, but you have the potential of being wrong if you don't put them. So yeah, so that's this one here. Right. So how are you guys liking substitutions? It's not that bad, right? Am I right, or?
You're right.
Yeah, which is good. You guys are better than me. When I first learned substitution, I was like, huh? It took me a good few days to actually, oh yeah, I got it. Yeah. You guys, that 1 day turnaround. This is good. All right, so now we have one of these guys, and we have numbers on the integral. Now, hopefully you know what that means. Right? So this guy here, this is what we call a definite integral. All the others were indefinite. And what makes it definite is because there are numbers on the integral sign, right? Now, there are a couple ways to actually do this, and I'm going to discuss both of them. But I guess I will have method one being whatever one of you guys tried. So maybe someone here can tell me what they did, and then I'll show you a variation on this that some people might actually like. So yeah, maybe someone tackle this one for me. How did this work?
Okay, so I did u equals ln x,
Mm-hmm.
and then du equals 1 over x dx.
Yep.
And then I just plugged into u to the original equation, so it would be u over x times dux.
Oh, right. So we have to. Let's actually rewrite that. So this would mean that dx, multiply both sides by x, is equal to x du. And so now we can plug that in. So ln is u, the
Over
x stays, and then we have x du, and the x's cancel. Okay, and then?
You find the antiderivative of u, which would be u squared over 2, yeah. And then you just plug in the original equation, so ln x squared, so not the x, but the, yeah, and then over 2.
Okay.
And then that's what I got.
But we're not it's not complete here, so you're missing stuff. These numbers, what do those mean?
Do we have to subtract e? Do we plug in e and then subtract by 1? So we
Yeah,
plug in e.
so what you're forgetting here is that you should write this line,
Oh, okay.
and then you put the e and the 1. It's also worth mentioning that you should keep the numbers on the integral here. Now, because you're changing to the variable u, it's going to be important for you to keep track of the variable. So if you're leaving the 1, so you're here going to identify, oh, I'm looking at x equals 1 up to e of this function. And again, x equals 1 up to e of this function. So to show that these numbers, 1 and e, you don't plug them into u's because they're not u's. They were from the x's. Once you translate back to x, you can just put 1 in e, and now it's just the fundamental theorem of calculus. Take the top number, plug it in, minus, take the bottom number, plug it in. Now, this guy, these guys here can simplify. Ln of E. What's ln of E?
1.
It's 1. Ln of 1?
0.
0. So a half is the answer. Okay. So that's one way to do it. So the only difference here is, of course, you have to apply the fundamental theorem of calculus. So this is pretty much staying it's pretty much comparable to what we were doing before. So you have this guy, it doesn't look like a basic rule, can't really simplify it. So you do a substitution, plug it in. However, you have numbers on the integral here. You have to keep them with you because you don't want to forget applying this step. Now, one option, which we now denote method 1, is to just leave the numbers in terms of x's and wait until you plug in the x's before you plug in the numbers. So that's one option, right? And this is how it would look. So very similar to what we were doing before, bring it all the way to the last step, what we would have done here, but instead of plus c, you will have these numbers to plug in. So that's the fundamental theorem of calculus. Now, method 2 is, for the most part, it's going to be the same. The difference is how we treat the limits. Now, this is another option. Neither one of these is more correct than the other. So you are just going to follow along with whichever one you prefer, and it'll be okay. So here is method 2. Method 2 is saying that we are going to change the limits. So that is going to be the difference. So this 1 and this e, you're actually not going to leave them in x's. You're going to change them to u's first. And here's how that would actually work. You start with u equals ln x, as always. Your du would be, of course, 1 over x dx. That's not going to change. And so now you have a little section where you're going to say, we're going to change the limits. And basically now what you're going to want to do is convert these numbers, the 1 and the e, which were x's. You want to essentially convert those numbers to u's. So you're going to say, well, when x equals e, my u is going to be, well, you're going to plug in x, ln of e, right? So you're gonna just plug that in. X equals e, u is ln of e. So this means that u is equal to 1. Let me move this chat box out the way. Can I put it over there? Then when x equals 1, you would plug it into the substitution equation. U equals ln of 1, which we now know is 0. Okay, so you can change the limits to do this. Let's see if I can get this in. Use substitution equation, which is this guy. So when you change the limits, you use your substitution equation, u equals blah. You're going to plug in the x's in that expression and find new numbers. Now, what does that get you? Well, now you're in a situation where you have new limits to go along with the new variable. And this will actually save you from the back substitution. So everything else is going to look the same. You're going to have this u over x times x du. But on the limits here, you're going to have the 0 and the 1. So you're going to have 0 here, and you're going to have 1. And I don't need to say x equals this because these numbers correspond to the du. So now, essentially, you just have the integral 0 to 1 of u du. And at no point is it necessary to go back to x's now, because this is completely in terms of u's. And so I can have u squared over 2 between 0 and 1. Take the 1, plug it in, I get a half. Minus a 0, plug it in, I get 0. So I get a half. So you'll notice here in this situation, back substitution not necessary. Right. So there are a couple ways you can deal with definite integrals that require substitution. One, and probably most people would like this, just go through the motions as you always would have, but you have to make sure you get back to the x version of the answer before plugging in the numbers. A common mistake would be to plug in the numbers too early. If you plug in the e and the 1 into the u, that is incorrect because u is not e and 1. So you can just do it as usual. Once you get to the answer purely in terms of x's, you don't put a plus c. You write this notation and plug in the numbers, apply the fundamental theorem of calculus, and that's it. Another option is to change the limits using your substitution equation. And then from there on, you only think in terms of u's. There's no need to go back to x's. Okay, so these are just two options. Both methods are fine. So I'd leave this up to personal preference. Now, there are situations in which the second method is preferable, but those situations arise in Calc 2. So it's not something we have to worry about now at all. So pick whichever method you'd like and always do it that way. It'll be fine. Now, any questions on either of these or what we were doing here? Are we good? Or questions? Comments, concerns? Okay, we're going to move on then. But that's integration by substitution. Here's an example of doing it with a definite integral. You have a couple options here. Do everything as usual, but at the end you have to apply the fundamental theorem of calculus, plugging in these numbers. Or you can change the numbers on the integral in the beginning and then just plug it into the u version of the answer. Either one is fine. Method 2 would be preferable in certain situations for those of you in Calc 2. So if you're going into Calc 2 and you're doing something like a trig substitution, I would definitely recommend method 2 because it would literally cut your work in half. Here, it's not a big deal. Yeah, so that's pretty much substitution. And you guys did most of the work here. So I think for the most part, you are okay here. So that's that. And again, I'll post a PDF of this guy in the video description. For now, let's on to the next thing. So what I want to talk about to kind of wrap up the semester is some applications of integrals, not a lot of them, right? So we did a lot of applications with derivatives and we spend a long time on that. Applications of integrals, you really would tackle this mostly in Calc 2. And you'll tackle integration in general and applications in Calc 2. But I want to talk about a few applications, a few reasons why this might be useful. So you might realize that, okay, so fine, we can do a derivative backwards, whoop-de-doo, right? Or I can find an area under a curve. Why do I care? So I'm mentioning here a few applications about how you can use them. And I at least want to get through the first one, the physics application, that equations of motion. So you might already see this being applied in physics classes if any of you guys are in physics. In physics 1, usually like chapter 1 or chapter 2, you do a lot of problems like this, and they have a lot of formulas in that book, and almost all of them was derived using calculus 1 and antiderivatives, actually. So I'll give you an example problem here. Here's a word problem. So this would be like a word problem that you'd have to do. And I'll talk about how we'd actually go about solving it. Maybe I can make this a little bit bigger. Okay, so here's a physics example as it applies to motion. What do we need to know about motion? So there are some things that I mentioned before. So let me actually talk about that. What we need to know. About motion. And this is just like movement, like position, velocity, acceleration, etc. So we did talk about this, but I want to jog your memory here. Suppose you have a function that gives you position at time t. Normally we'd denote this by s. So s of t measures the position of some object at a certain time t. Okay. Then it turns out that if you were to differentiate s, you obtain what's called the velocity function. And this is pretty much how fast the object is moving. And there's an indication of the direction that the object is moving in as well. So to obtain a velocity function, if you know a position function, you just differentiate. Now, if you differentiate the v of t, so if you differentiate again, you get what's called the acceleration function. So this is a measure of how your speed is changing. So this is the position, where are you? This is the velocity, how fast are you moving? This is the acceleration, are you speeding up or slowing down, right? So these will answer different questions. This answers the where, this answers how fast, and this answers, is it getting faster or slower, right? So these are the 3 important functions in motion. Now to move down this list, you obviously differentiate. Now, of course, we know about integration, and the fundamental theorem of calculus actually tells us that these guys are kind of reverse operations. They reverse each other. The antiderivative will tell you about the derivative, and they actually reverse each other. And that's why we can use all these derivative rules as antiderivative rules. We can just reverse the power rule and all that good stuff. That's from the fundamental theorem of calculus. So the fundamental theorem of calculus tells us if we want to reverse our direction in this list, we would integrate. So moving down this list from position to velocity to acceleration, you differentiate. To go back up the list, you can integrate. So this is an application of integration, because it's not all the time that you'll know about position and velocity and acceleration in this order. Sometimes you know about things in the reverse order, right? So now on to the example. So that's just a quick refresher there of some important concept. So we definitely discussed the concept of differentiating to find these new functions. Now we also know how to go backwards, integrate to find the other guy. When would we need to do that? So here's something. Group of angry calculus students throw Jhevon off a cliff. Okay, cliff is 500 feet tall. He's thrown off with an initial velocity of 10 feet per second. Okay, so velocity when it's positive, in vertical motion, we usually think of the positive as the upward direction and the negative as the downward direction. So this means they literally threw him up off the cliff, right? So the cliff is here, and it's like pew, they threw him off the cliff. So okay. Neglecting other factors like air resistance and all that stuff. Assume this is some ideal situation. The cliff is in a vacuum or whatever the physicists always say. Find his position t seconds after he is thrown. When will he hit the ground? Okay, so we want to know, find a function that's tracking my location and then tell me how long before I hit the ground, right? So these are the questions. Okay, now it turns out we don't know position. In fact, you want to find the position, which means you don't have the position, which means this function here, you don't have. You also don't have this function, by the way. You only know the velocity at a certain specific instance. You know the velocity in the beginning. You do not know what is a function that describes the velocity the whole time. So you also don't have this function. However, one thing that you do actually know, whether you know it or not, I'm going to tell you now that you know it, you do know the acceleration function. Because unless Jhevon has a jetpack on his back, he is under the influence of gravity. And gravity has a known acceleration. At least its average acceleration across the planet is known. So here are some things you also need to know. Maybe I'll put that up there. You should also know the acceleration due to gravity. And that's A, some people call it G, but let's call it A, is equal to, there are two units that you should know it in, feet per second squared. And you should also know it in meters per second squared. Does anyone know what these numbers are? Either meters or feet, acceleration of gravity?
I believe it's negative 9.8 meters per second squared.
Right, so it's 9.8 or 9.81. 9.8 is usually good enough, right? So 9.8 is usually good enough. 9.81. It actually varies across the planet. This is actually an average of the influence of gravity, but whatever. So yeah, it's 9.81 meters per second. Does anyone know feet per second?
Negative 32.
It's 32, right? So these will not be stated in the problem. You'll actually be assumed to know this. So that's another thing. So it turns out in this problem, in this word problem, the only thing you actually know for sure is the acceleration function. Area between curves, that's going to be the next application. We won't do that today. So right now, what you know is the following. No. One, I know that my acceleration function is, because it's measured things in feet here, the cliff is 500 feet tall, feet per second is velocity, I'm going to use the 32 number. So that's what I know. The acceleration due to gravity is a constant minus 32 feet per second. I also know a certain velocity. I know the velocity function at time equals 0. That's the point where I was thrown off the cliff. We'll call that 10. I also know that the cliff is 500 feet tall, which means that I know the position function at time equals 0 is 500. So these are all my knowns. Now, ultimately, what I want to find is I want to find the position function, and I want to find time to hit ground. So let's go. So we know that the acceleration function is minus 32, which means if I want to go up to the position function, I need to move in that direction, which means I should be integrating. So what I'm going to do then is my velocity is going to be the integral of the acceleration. So that is the integral of minus 32. What's the integral of minus 32?
Minus 32x.
Yes, but the variable is t here, but yeah. Plus c, don't forget the plus c. Now, the plus c, it's an indefinite integral. So we need to actually know what this function is. But this is where this is going to come into play. So since I know that v of 0 is 10, what that means is I get 10 when I plug in t equals 0. So of course, that means that c is 10. And so ultimately now I know my velocity function, v of t, is going to be minus 32t plus 10. Yes. Okay, so now I know my velocity function. And again, we're going to do this kind of thing one more time. Go to the position. I know the position is going to be the integral of velocity. So this is 32t plus 10. That's going to be minus 16t squared plus 10t plus another arbitrary constant, which we can find because I know that s of 0 is actually 500. So now since s evaluated at 0 is 500, this means that 500 is the answer when I plug in zeros for t's. So this means that my c in this case is 500. And this c is different from that c. You can call this a c1 and a c2, but it doesn't really matter. So s of t, the position function, is minus 16t squared plus 10t plus 500. That's one of the answers. This is your position function. That would describe the position at time t, where t is in seconds. Okay. Now on to the problem of when does Jhevon hit the ground? What do you guys think? How would you actually go about computing that?
Would it be like when you calculate when the velocity is 0? So like you would set the equation equal to 0 and find what your t is.
Why
The position
velocity?
function
Come again?
equal to 0?
You'd want to set the position function equal to 0 here. And here's why. Because the moment you hit the ground, your velocity is 0 after you hit the ground, right? The instant you hit the ground, you're actually moving at a certain speed, right? So you don't want to set velocity equal to 0 because that's just like after you're on the ground and you're already there. Also, I would want you to note that velocity would actually equal 0 at the top. You're moving up. You would literally have to stop in order to turn around. So velocity equals 0 usually indicates the top of the function. Now, there are other reasons why you would know that would be true. Velocity is the derivative of position, and we know that when the derivative is 0, that's a critical point. Critical points can be either endpoints of an interval, which is like he's already on the ground and he's dead, or they can be maximums and minimums. So the maximum, if the question were, what is the maximum height that Jhevon attains? We know we threw him up off the cliff. V equals 0 would actually be how we'd go after that. V is not 0 the moment you hit the ground. V not equals 0 at moment of impact. You're actually moving at a certain speed because you're accelerating due to gravity. Gravity is actually speeding you up. Okay. So when you want to talk about being on the ground, it's much nicer to describe that in terms of position, because on the ground is a position. So I would say here is that we want S of t to be equal to 0. And then no calculus here, really. It's a matter of solving this quadratic equation. So your t would be minus b. I didn't even check if this factors. It probably does factor. Does that factor? Yeah. Minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So you would have two options here. Your t is going to be minus 10 plus the radical of 100 plus 4 times 16 times 500 over minus 32, or your t equals minus 10 minus the square root of 100 plus 4 times 16 times 500 all over minus 32. So, moment of truth, are both of these correct?
No, I believe just the second one would be.
Right, so this one here is reject. It'll actually be negative, so this is negative time, which we're not in quantum physics, so let's not worry about that. And so this is going to be the answer that we want in seconds. Right, so the top is going to be negative and then you divide by a negative. So this is definitely going to be some positive number here. And I mean, I'm not allowing you to use calculator, so I would actually accept that as the answer. But I suppose if we wanted a decimal approximation here, that's around 5.9 seconds. But that's that. So, yeah, we'll do with these guys next time, a couple other applications, but I don't even really want to talk about anything after that. So we're pretty much wrapped up. So we can knock these guys out of the way on Friday, or we can talk about your test on Friday and then knock these out on Tuesday. Either way, this is less than a lecture worth of material, I would assume. What I would suggest doing for now is to practice mock test by tomorrow, which means, again, I do want you to pretend it's a real test and actually take it. So spend today into tomorrow studying for a bit, and then actually try to do the test by like tomorrow night, 4/23/2020. And if necessary, you can discuss with me in class on Friday.
I have a question for
Yes.
the test. Like, do you know like if you're gonna administer it like during a certain time period? Because I have a final that same day. So like just so like I could
On
organize
Wednesday?
times. Yeah.
The Chem Lab final is also on Wednesday, which
Yeah, me
that's what you're
too.
talking about. That's on
Yeah.
Wednesday. It would normally be after the time frame to take that would normally be after your class anyway.
Yeah.
So that shouldn't that's what's going on with that.
Yeah.
So do we have a conflict with this time and that final or no?
Like there's like an overlap of like 20 minutes, but like they just give us a period between like 12 and 5. But like I don't know if you're still gonna administer it during our class time or like another time or something.
Oh,
I just
are
wanna-
you, what's your class time? Are you in the,
I'm in the 11:30 to 12:20 class.
okay.
I mean, I can still take it and then I'll just take it like after, but I just
Yeah.
wanted to make sure.
I
Unless
mean,
you're
I
like
think
doing
it's
it
fine.
earlier or something.
Not really. I might have an option of doing it earlier if anyone from the the earlier section can't make this time.
Yeah, I know a lot of us also, a lot of us have that chem final that day, and I know that there is that little overlap. So like if you're in the 10:30 class, would you take it before?
So there is a 10:30 class, right?
Yeah, I'm in the 10:30 class.
Okay, so yeah, I would actually try to administer an exam in the 10:30 slot as well.
Okay, thank you.
Yeah. So when it comes to exams, I'm kind of going to leave it up to all, do one for each class slot. So yeah, so there you will be able to take the exam either 10:30 to 11:30 or 11:30 to 12:30.
Okay, thank you.
All right, that's being said, I guess that's it. Let's wrap up. So go over things in the study guide and try the mock test. And if you have questions on that on Friday, you can let me know. Other than that, I guess I will see you guys. Oh, all right.
Thank you.
Thank
All
you.
right.
Bye.
Thank you.
Okay, take care.
I just had a quick question.
Oh, yeah.
Yeah, it was real quick. So the test is gonna be administered on Blackboard?
No, but it is going to be online. I'm
okay.
still working on the details. I'll send you guys that as soon as I know it. I'm meeting someone tomorrow to actually work out the technical details.
Oh, okay. Thank you.
Yeah. Okay. All right. Cheers.